All right, let's start. Yeah. So I just released the 2 new extra challenge to have an homage to some of the game. So do you guys know this meme? Yeah, so like we need to pay respect. Like I want to pay respect to your shellcode. So like the challenge is something like so the challenge will ask you to submit a shellcode, and then this kind of the 2 byte code. What it will do is like in every 2 bytes of your shellcode, it will insert character F. So you need to avoid all those kind of the noise. Yeah, but you can write the shellcode to successfully run BNSH and then set RegID, everything. Yeah. So your task is like avoiding this kind of the error. So the challenge is from like I'm not sure like you guys are aware of like when you send a packet over the network, there could be some error. Yeah. So we use HTTPS, and then that actually check all the integrity and others. So if there's an integrity mismatch, then we will ask like a resend of the packet or something. But in reality, we are not using SSL for shooting some of the exploits. Yeah. So in that case, there could be some of the noise bits comes in. But the important thing is like we can write noise resistance shellcode. So the implication of this challenge is like that you can practice that. Yeah. And then I know it's a little difficult, so like it's an extra credit challenge, so you can have fun with that. So, and this is not about the ASRL and another thing. So it is hosted in VMCTF1, and you can run fetch week 5 to fetch the challenge. And then this just have a little respect. And then the second one is a 1 bytes code. So it will have pay more respect to your shellcode. And then what it will do is like it will insert F every single byte. Yeah. So you need to be very careful to write your shellcode, but you can still write your shellcode that runs a BNSH. Yeah. So if you finish it playing with the other challenges or stuck at somewhere, then please use those challenges to your brain to get rest. Yeah. Any questions for those 2 extra credit challenges? It'll be fun. Yeah. Then, so students on Zoom, can you see the slide? All right. Let's start. We will continue to run how we can use ROP. And one thing I will tell you is that ROP is Turing complete. So what that means is that we can write any kind of program using ROP chain. So we can implement anything. Alan Turing defined like what computers can do. So because ROP is like a Turing complete, and then how we can prove that is like if we can implement some of the language interpreter that is Turing complete with this, then it'll be Turing complete. And then can you suggest what would be the easiest way to prove that? Yeah, so that we can actually implement the brain fog interpreter with ROP chain, then it will be Turing complete because brain fog is Turing complete. Yeah, nice. Yeah. So please have the implication that like the ROP gives you a capability of the running arbitrary program on the victim's memory space. So it's something like opening a Python interpreter for you. Yeah. So that's how I regard ROP. Yeah. So let's do a little bit of a recap about what we ran on Monday. So for ROP 164, because 32 is quite easy because you can put all the values on the stack. So you have a lot of freedom to set the values for the arguments. But in 64-bit, you need to find the specific gadget to pop the register to set the value from the stack. So we start with the pop RDI and return to set the first argument like this. And then there is a gadget that does pop RSI, pop R15, but we don't care about the R15. So we can use that for setting the RSI and then call set read ID. And we can do the same thing for the exact VE. So set the address of the sum of the string or binsh or set RSI RDX is 0, then exact VE. Yeah. So you can regard like a chunk of this stack values are like something like equivalent to this kind of the function call. So if you have that in mind, the ROP is not a difficult animal anymore. Yeah. So it's just like you just write what kind of function you want to call, and then translate that into the stack values. You just put that and concatenate that. So what's matter is like how many bytes you can overflow on the stack. So there will be some of the challenges that with the limited the stack contents or something in week 7, but you don't have to worry about that for now. Yeah. So the most of challenges I will let you like run have enough space to write your ROP chain. So that's why we call it as a ROP chain, because we can chain function calls arbitrarily. So the basics about the chaining the execution is that for 32-bit, so we can get a function and then set the argument on the stack. So we can have up to n numbers of argument if we have a n number of a pop return gadget. So, and at the end of this lecture, I will show you how you can find like the 6 pop and return easily. And then that is always in the C program if it is compiled with the GCC or Clang on Linux or Unix environment. Yeah. So we can use that. And I just try to express some of the chain, something like a regular expression. So we can repeat this 0 or many times, and then that will be composing the ROP chain. And for the 64-bit, we need to have a different gadget pop to the specific register. It could be pop some other registers, but we can control that by filling some of the paddings or filling random values or arbitrary values to the uninterested registers. And another thing to note is that like not just for AMD 64 or x86, so another popular architecture is ARM because runs on this device, and then like some of you have like the Apple M1 or M2 processors, so they are running the ARM V7 32-bit or like AARch64, which is a 64-bit ARM, and their calling convention is somewhat similar to 64-bit Intel, because they will use X0, X1, X2, X3, those registers to pass the, actually X0 serves as a return value. So like it's something similar to EAX, RAX, but X1, X2, X3, these are like some of the argument order. So that's more elegant and neat. Yeah. So when you get to like the pounding the ARM binary, then you can remember that what you have done in 64-bit, you need to find the gadgets to popping the value from the stack to specific register. Yeah, then you will see that a lot of similarity in ARM architecture and then 64-bit architecture of Intel in terms of the writing exploit. So the implication of that is like after learning about ROP on AMD 64, don't be afraid about like using the same technique on the ARM architecture, because conceptually it's the same. So I'm keep emphasizing that the ROP is a new programming language for hackers. Yeah, so it's esoteric, I know that. So, but you can easily convert any kind of function call like this in 32-bit and 64-bit. Any questions about this recap? So I told you that like we practice like the launching buffer overflow attack in week 2, and then the week 4 week 3 we injected shellcode, and then we learned about how to defeat the defense in week 4. But now you will realize that using ROP you can solve almost every like the rest of the challenges, right? But how I think is like because you have learned it step by step, like week 1, 2, 3, 4, then that's why you can feel it like a ROP is easy. Yeah. And I'm a believer that anyone can hack. So and give a little bit more hint about the ROP 2 challenge. So what it requires is like there's no exact PE, but don't worry. While executing the sticky spit binary, like a challenge binary that we have, your execution environment will have a group ID of that binary program. That means you can read the flag. So the purpose of hacking is like stealing some of the information or overriding some of the data to like take control of the system. So one of the easiest ways is like getting a shell, because you can execute any kind of command afterwards. But in some cases that could not be possible. But in that case, we just focus on our goal, stealing the flag. So in that case, we don't have to launching the shell, just do open, read, write. Yeah. So open the flag, read the flag data to the buffer, and then write out to the std out stream. Then you can read that from like the program's output. So basically in ROP 2 challenges, you need to call these 3 functions. And specifically, how you can do that is I demonstrated that you can easily find some of the existing string on the binary program. So it could be for, at, and any kind of thing. And then we can even use D030. These numbers are like the octet string. So it is like the 24 in the decimal, and then it's 18 in hexadecimal, right? Yeah. So if you can copy and paste this one and then create the symlink using os.symlink in Python, so you can create that one. But there's a human readable and typable thing. Like, why not use that? So that's the thing. So the exploit sketch is like you can create the symlink to flag to 4, and then run open the flag, and then by the system principles, we don't use randomized file descriptor order kind of thing. So whenever the Linux kernel creates a new process, it will create the file descriptor 0 as a standard input, file descriptor 1 as a standard output, and file descriptor 2 for standard error. So 1 and 2 are for output. And then, so that's why on like the write function, I put 1, because that will be standard out. So if you write on some of the content in there, then you can receive that from the Pontool script, or you will see the output from the console, because that is standard out. And then, so program will occupy 0, 1, 2 as a file descriptor. And then the first file we will open in the program will have the next file descriptor. So that's actually 3. Yeah. So how can you solve this? It's like just call this, and then fd will be 3, because open will always return that value. But I would like to emphasize that even if I tell you something like this, don't trust me. Please try to observe like what kind of values are returning from the open after calling open from GDB. Then trust what you see at there. Yeah. So I got questions like some of the students say like oh, I followed your guideline on the slide, but it doesn't work. But I always reply back that check in GDB. Yeah. Then you can easily find like how it works. Then yeah. And then another important thing is like if you just follow the slide, you're not getting the details. But if you examine in the GDB with the line by line execution of the assembly, then you will see all details about that. And then that's the thing that you should learn. Then after consuming all that kind of the knowledge and information, then you will be a great hacker. So summary of like the how you can write an exploit is something like this. Yeah. Any questions for ROP 2? All right, let's move on. So we will cover like, some of the exploits sketched for ROP 3, 4, 5, 6, and ROP 3 challenge. And like I highly recommend that whenever you see new challenge and try to run pawn check stack, because this is a tool from the pawn tools, and you can see that what kind of protections are enabled to the binary. So for both 32, 64, these are conceptually the same. Architecture is just the difference. And if you see that, it has a non-executable is enabled, so you cannot run any kind of shellcode. That's not true. I'll tell you the detail. And then, so you must use ROP first. But this challenge asks you to run your shellcode. Yeah, it's quite ironic, but you will see that it's not ironic at all. And another restriction is that this challenge runs change directory first. So no matter which directory you run the challenge, it will change your current directory to the root of the file system. So if you create the symlink 4 in your directory, then you cannot read it with just putting 4, because your current directory is the root. You need to type a full path. So like I'm a bad guy. I intentionally blocked that kind of the method to teach you another method for that. And another thing is like I'm not sure like how many of you use the path trick in solving like the DEP1. Yeah. So if you don't know how to solve the DEP1 with the regular method, then please check with the path variable. So what that means is that like in that challenge, it runs a system ls. But how the system find ls is like from the path environmental variable. It visits each directory and then where the ls is. But if you set the path priority of your current directory as the top priority, then it will find the ls first from your directory. So if you put a ls as a binsh, then you will see that that is executable. That is executing as a result. But I also blocked that approach. So it will remove path variable, so you cannot play with that. It's quite ridiculous, right? Yeah. So the restriction is that you cannot execute the stack, so you cannot use shellcode at the first place. And then there's no system function, there's no setreg, and then I moved all of you to the root of the file system, so you cannot use symlink. But there is a beautiful function name called MProtect. And then we can run MProtect using ROP. And to give a little idea about like what it does, so whenever you're curious about some of the function in C, then you can just type the man MProtect on the server, then you will see this kind of the description. So it's quite interesting. It sets the protection on a region of the memory. So in short, what that means is that we can change the privilege of the memory. So your stack is readable, writable, but non-executable. But we can make any area executable by changing the permission. And then the protection flag is a read is 4, W is like a 2, and then executable is 1. So if you put 7 on there, then you will have a read writable executable area for that. So target is you can set any kind of the valid memory region. Yeah. And then you can set any kind of area that you can write. Then you can put your shellcode in stack or somewhere else. And it can be anywhere, but in the challenge, you can put your shellcode in some of the global buffer area, because it will kindly accept your input to the global buffer. And then your task is run MProtect to release the permission restriction to make the entire global variable area as executable. Put your shellcode in there and run it. So the usage is something like this. So you need to call MProtect address size protection, but the memory permission is managed in page granularity. So memory page in modern systems represent for the 4 kilobyte block. And then that's actually 1000 in hexadecimal, 4096. So one of the restriction on calling MProtect is like the first argument, the target address must be aligned in page size. So what that means is that you must have like a 30 at the end, yeah, to successfully call MProtect. So even if the like some of the global buffer address is like 8048, 123 or something, to make it executable, then you need to set it as like the target address is like a 000 at the end, and then the size of the MProtect need to be multiple of the page size. But from the VM map on GDB, you will see that that's only 1 page or 2 page or something. So just put that size. I believe 1 page size is enough. So if you call this address and then size 1 page and then 7 as a protection read, write, execute, then you can change the permission of that memory region. So I provide all the source code for all challenges, so you don't have to do reverse engineering. That's not true. You need to check that to get the exact address and then where the buffer is or something like that. So, but I want to give like a little bit more like the conceptual idea to the challenge. So that's why I put the source code for that. And the input function of the ROP3, what it does is like it will get a stack buffer and then you can overflow this buffer. So that's where you can launch the ROP attack at the return of the input function. But at the same time, what it does is like that it will copy the entire buffer to the global buffer. Yeah. And then this address is not randomized if the binary address is not randomized at all, because that's the data area of the current program. And then like the data will be not randomized for the non-PIE binary. So you will naturally know what is the address of the global area. So the one trick is that when returning from input function, if you call MProtect to release the permission restriction for the global area, and then returning to the global buffer, then it will start executing start of your buffer input. So how you can exploit this is, so you can write the payload as you put the shellcode at the start of the buffer. So it must be smaller than the buffer size of the input function. And then you fill the buffer up to save the EVP. And then at the first return, you need to return to MProtect. And then for the argument, you can set it as a target address as like a global buffer address aligned in a page granularity. That means 30 at the end, and then 1 page size and 7. Then it will call MProtect, and then it will return to gbuff, the global buffer address. Then it will release the permission and return to the global buffer and start executing your shellcode. And then you can do the same thing for the 64-bit shellcode, and then buffer fill up to save the RBP, and then argument setting should be done first. Pop RDI, global buffer aligned, set RSI like this, set RDX like 7, and then call MProtect, and then call global buffer. Yeah. Any questions for our ROP3? Yeah, it's quite straightforward. So the implication of this challenge is that like even if there's no area that you can execute and writable, so we run it as we learned it as a writable XOR executable, so we can break it using MProtect. Then how do you think about the defense of like this kind of the method? What would be the naive defense for this kind of attack? Yes.
You could destroy the function and replace it in the library.
So it's more like the do not allow MProtect at all. Yeah, it could be. And then it could look silly, but that's actually implemented in iPhone. Yeah. So in iOS device, so when you try to run MProtect with the executable flag enabled, then the iOS kernel will reject it. And then the only application that Apple allows to do that is Apple Safari browser. So there is a special permission. So in Apple's term, it's called entitlement. And then there is a code generation entitlement in Apple. And then Apple disallows having that in public app store. But they can do that. So the important thing is that, so modern web browser uses JavaScript inside of that. And then if we interpret JavaScript, it's quite slow. And how Google Chrome or Safari, Firefox, all those like the performant web browsers are doing is so-called the just-in-time compilation. Have you heard about that? Yeah. So whenever there's a JavaScript code comes in, and then it will compile it into the native code as a machine code as a assembly, and then run it. So it's not about like the interpreting the JavaScript code. But if we disallow MProtect, then there's no reason that that could be writable and executable. So the implication of that is like a Google Chrome and iOS, Firefox and iOS, they cannot use JIT compiler. So if you run the browser benchmark on iOS, you will see that the Apple Safari is super fast, while the others are a little bit slow. Yeah, that's happening. Yeah, but that was like that could be released if like so in iOS there's a so-called web view. So when you are implementing the application, you can have the browser kind of the UI. So you can just borrow what Apple Safari uses. So in that case, like because that is like the coming from the different process, and then UI is just showing up. So we can use like the Safari's JIT compilation in a separate process. But that will result in like the just same as a Safari. So some of the browser vendors, they want to use their own layout or something. So in that case, like they need to implement their own way to run the JavaScript or something like that. So in that case, they might be slower than that because they cannot use JIT compilation. So that's some of the trade-off between the performance and security. And then like the Apple claims that the Safari is the fastest, and I'm not sure. Any questions about that part? And then if you upload your app with the code signing and then code injection entitlement, then the Apple will immediately reject your app from the like publishing in the App Store. Yeah. All right. So next is ROP 4. We have a very simple challenge. Yeah. So it has a read buffer for big size. I'm giving a big space for the rock chain. Yeah. And then just return. And then you'll be curious why we do have like this kind of a string. And then this is very important because I do the same thing in the ROP 4. So your current working directory will be the root of the file system. And then I set the path to the bin and user bin where you cannot write without root permission. Yeah. And then run it. So the implication of this one is that, so it has open, read, printf, those kind of function, but it does not have exec.v, no system. Yeah. And also it does not have MProtect. So you need to use ROP to run, open the flag, read the flag, and print the flag. So this is somewhat advanced version of the ROP2. Yeah. But the important thing is like you cannot use symlink. So you need to use full path to open the flag, or there's some other trick. You can shorten that, but at least you need to build a string that is not existing in the program's memory space. So you cannot use at number 4. Yeah, that's the restriction. So this is the difficult part. But you can create arbitrary string using ROP. And the method is using string copy. And what we will do is something like this. So I kindly put these strings. So I forgot the name of like this kind of string, and then it contains all to A to Z in one single string. Yeah, that's why like some of the font comparison, we use that string for that. And then I also put 1 to 0 and then dash or something. So you will have all the characters required for your username or something. Whose username includes a capital letter? Do you have that? Yeah. Then try to create the symlink on /temp. I'm giving another hint. You can make all the things a lower character and the numbers or something. Yeah. But what we will practice in this challenge is like we will create an arbitrary string using string copy like this. And some of you have something in mind, and then let's get into step by step. So the first thing is that we need to find a place to build a string. So just run vmap on the GDB and then try to find any kind of a writable area and then not use the area. So that to be safe, if the region is starting with 8048 A000, then just put 8. It will be like in the middle of the region. Yeah. So that will be some of the place that you can safely write any kind of value. And then let's build a string using the string copy. So we can call string copy to target address. And then if we know the address of the string, it will run string copy using the ROP chain. So it will put the string on the memory. Then how you can build the arbitrary string is that. So I just like simplify the example. So suppose you want to build a string sh. Then from the string, you can find there's an S character in there. So from the base address of that string plus 24, which is the like the location of that S character, put that. And then you can check that on GDB. So it's an S over lazy, but we don't care about the rest of the string. And then we will run string copy to target address, starting from copying the starting from that position. Then the result will be S over the lazy dog, something. And then to attach H on top of that. So our target will be +1. So we will keep S, and then we will copying the data starting from the next byte. And then we will find H, and then put that address. And then it will copy starting from H. So the important thing is like the 1 byte going over. So the result will be S is there, and then H is there, and then rest of the strings are there. And then how you can terminate a string is that we can copy 0 bytes using string copy 2. So at the end of the string, there always be the 0 byte. And if we put that address, it's something similar to we are copying the null string to the target. So it will kindly place 0 byte for us. So run string copy +1 again, null string, then it'll be terminated like this. Now you see that there's something similar to this. Yeah, we are not a Zodiac killer, but like we can play like this kind of thing. Yeah, in the ROP chain. So ROP 4 requires you to build this kind of the full string. Yeah. So you can target like the real directory, or you can target your home directory, or you can target the /temp something by creating symlink. Use any kind of method to run open read and then printf, because flag is all like the printable bytes. Then you can see the result. Any questions? If you can find that, you can use that. Or yeah. But I'm not sure, but you can find it. But you don't have to use that, because you can read the flag directly from the full directory here. Right. So if you run fetch, that will be symlinked to in your home directory, but you don't have to worry about that. The full path of the real flag do not have the capital letter. So, any other questions? And then, can you feel why I set the higher points to the challenges like this? Yeah. So now you will run the real things. Yeah. And the next is like about the general idea of like a ROP. And that is required for ROP 6. So I will cover ROP 5 at the end. So let's cover ROP 6 first. So in 32-bit, we can call any kind of function that has n number of arguments if we have a pop and then return. Yeah. But we don't have to restrict ourselves for finding pop return. And then, so one of the interesting area in every C program compiled with the glibc library, so that's somewhat de facto standard for every single Unix or POSIX machines. So it's not on Windows though, yeah. But in Mac OS, FreeBSD, Linux, or Unix compliant machines, yeah, they do have this kind of area called the libc CSU in it. Yeah. So what if this is actually like, do you know that the C language has a constructor? So C++, they definitely have a constructor for object, but the C language do have a constructor, and then that constructor is for whenever you load the program or load the library, it will automatically be executed before starting the program of the main. And then that's why we have a libc start main. So libc start main will run every single constructor that we have, and then it will run main. And then this is existing in there because this is a C standard, but almost nobody uses that. But we can exploit that as an hacker. Yeah. And then we will learn about exploiting that later in week 6 and 7. Yeah. But at here, the important thing is like they do have this kind of function always there. And at the end of this function, you will see add 0xc ESP pop return. And then can you see this is equivalent to 7 pops and return? 1, 2, 3, 4, definitely. But the add 0xc ESP is removing 12 bytes from the stack. 12 bytes is like 3 blocks of the 4 bytes. So pop 1, 2, 3, 4, and then 3 blocks. So we can easily find pop 7 and return. So if you target that, then we can call like any kind of function up to 7 arguments. Yeah. So if you have something that requires 7 or more arguments, then like you can use that kind of trick. Or if you have more arguments than 7, then what you need is like the add something ESP with a larger value and then return, then that could be another gadget that you can move the stack. And finding some of the gadget, like the adding some arbitrary value to this ESP. So using that kind of gadget is so-called the stack pivot. So what that means is that right now we are playing with the stack for the ROP chain. And then if you jump to some of the weird instruction that add the larger value to ESP or arbitrary value to ESP, then we can actually change our stack to heap or other area. And then if your input goes to there, then we can actually do ROP using the heap area. So that kind of technique is so-called the stack pivot. Yeah. So we are not actually using the stack, change the value of the ESP with the gadget, and then on the heap or something. So I'm sure that some of you are not like clear about that, but we will have some challenge that requires that trig in week 7. Then I will revisit that, yeah, at that time. And then for 64-bit, yeah. In 64-bit, we don't need pop many, but what's important is that we need pops to specific register. Yeah. And then to run like the 6-argument function or something, then we need to find a pop RDI, pop RSI, pop RDX, RCX, R899, yeah, those kind of thing. But you will see that all those are not available in a small program. So in the small program, it just has like a pop RDI, pop RSI, but there's no pop RDX. Yeah. So I just mentioned that there's no pop RDX, but you see that pop RDX in our challenges. So in this case, I'm a kind guy. I kindly insert pop RDX with the inline assembly just for you. That's why you are seeing that the knob is here because I inserted it deliberately. So it is not generated in the compilation process. Yeah. So if I remove this function, then there's no pop RDX at all. But to run execv, you want to set pop RDX. Set the RDX value as 0. Otherwise, it will crash. Yeah. And then I will give you an idea that how you can control RDX with this. So there is no pop RDX, but what we can exploit is, so this is an example of the constructor in C. I'm not sure you have seen like this kind of the weird syntax or something. Then I use this a lot. Yeah, I'm not a developer, but yeah. So these kind of things are constructors. So like if we run this, it will print out I'm a constructor first, and then run main. So this is what I just mentioned about the libc CS unit. Yeah. And the important thing here is that how the program is being executed is from the start, it will call libc start main, and then it will call libc init first, and then libc init, libc CSU init, and then call main. And you will see all those kind of things if you follow from GDB from start, step by step. So some of the students think that that's time wasting, but I've done that a lot. And then I always emphasize, take a look at the detail, then your knowledge will be expanding, and then you can use that kind of knowledge sometime when you encounter some of the difficult challenge. Yeah, that will be very helpful. And one student asked me about the question that like so this class is quite difficult because like they cannot find what's the right way to do something. But I always emphasize that there's no one right way, and then there could be many ways. And then that students mentioned that like how can you find the right way? in 1 second or something. And then the students mentioning that like having that kind of skill is very important to learn cybersecurity efficiently. But I will tell you the secret. The reason why I can find not the one right way, but the shortcut is I failed more than 10,000 times. That's why I know that. Yeah. And then I'm a bad coach. I'm asking you, fail a lot. Then you will learn a lot. Yeah. And then like on Facebook, I've seen that one of the posts in like around 10 years ago or something. So my friend is working on the startup company as a CTO or something. And then he was frustrated with he's keep failing on getting investment to the company. And on one day, he's keyed, he's playing the game. And then it's something like Super Mario kind of thing. And then if the Mario dies, it says fail, says fail. And then he's Korean, so don't know about any kind of English at all. Yeah. So he asked his kid about but the kid was happy after he fails. So the dad think that oh, this kid don't know about the meaning of fail, so that's why he's happy. So he asked the kid about do you know what is the meaning of fail? Can you guess what was the answer? Yeah, retry, then you will succeed. Yeah, I like that. Yeah, so I know that we encounter failed and then we frustrate, but how I think is if I recall how I learned about hacking and all those things, because I was unfortunate because in 2008-9, then there's not that many cybersecurity professors, and then literally there's no cybersecurity professors in my college. So I learned most things by searching the internet, and then sending direct message to IRC, because there's no Discord and Slack, those kind of things. Yeah. So I mostly learn many things by my own, and then helping with the questions, with the interactions with the other hackers. Yeah. But in doing that, I experienced fail a lot. And then those failure made me up today. Yeah. So that's why I'm emphasizing that fail a lot. Yeah. All right, let's get back to the context again. Yeah. So important thing is that the libc CSU init will always be there. But the current focus is how we can set value of the RDX, even if there's no pop RDX, right? Can you see any kind of pop RDX? No. No. But you do see something RDX here, right? There's something RDX. Never thought about that's impossible. I'm always say I'm possible, right? Yeah, we can do that. So we can use this part. And then we learned ROP chain as a pop return, pop return. That's one way. Move, call. That means we can execute some of the code and then think about it. Can we control R12? Yes. Can we control RSI? No, RBX. Yes. Can we control R14? Yes. So R15D is 32-bit part of the R15. So we can control full 64-bit of R15. We can also control R13. So that means you can set RDI, so 32-bit part of the EDI, so you can set it 0 and then put the address. Yeah, that's possible. Yeah. So we can set first, second, third argument, and then call. I know this is a little difficult and sophisticated, but once you made it, You will feel that it's quite neat, and then ROP is super powerful. You will feel that. Yeah. And then to control RDX, exploit sketches, you need to set R13 as 0 using this gadget. Then that will make RDX as 0. You need to set R14 as a 0, then RSI will be 0 before making a call. So you need to set R15 as a string, but the R15D only sets a lower 4 bytes. So how you can do that is like there will be pop RDI. So set RDI as a 0 first. And then if you find the string into the code area, that will only use lower 3 bytes, 400000 or something like that. Then by setting the R15D into RDI, you can point some of the string. And then the difficult part is like how we can set R12, RBX, and something like this. Yeah. So if you make RBX, so this is a syntax that it's actually the R12 plus RBX multiplied by 8. But if you set RBX as a 0, then we don't care about the multiplication at all, and then addition at all. Then what matters is R12. So for this part, the syntax of that is like the B multiplied by C plus A. Yeah. So it's something like this. And then because it dereferences the memory and run it, yeah, you need to put the address that's towards the address of the exec VE. Yeah. But we can easily find that. I told you everything is possible. So set RBX as 0, then it will just dereference R12. And then it will get the address pointed by R12. And then if you set it as the exec VE, then it will not work because exec VE address will store this kind of value. So it has a 1 difference. That's important. So it will fail. So it will call to this one, and then this is not a valid address at all. Yeah. So it will generate the segmentation fault. So the important thing here is that we need to set R12 as an address that contains the address of the exec VE. Yeah. You will be having this kind of question, and the answer is yes. There always be. And then let me tell you a little detail about like how your program calls a library call. So we will specifically learn about the PLT, procedure linkage table, and GOT, global offset table. And then you don't need to learn about those detail at this point, because in week 6 challenges, it uses a lot, and then I will revisit that again. But the important thing here is like if there is a address that stores the address of the exec VE on your program's memory. So how we can run printf. So printf is not in your program's memory space. That is in the library area. And then before running the program, if you do the printf on GDB, then it will print out this section. So the address 4005A0, that's definitely the code address, but it says printf at PLT. The PLT is procedure linkage table. So this is actually a fake printf, not the real printf. Because to call a function, we need to have some of the location and in some of the address. So that's why the program has a placeholder as a gateway to printf to actually call printf in the library space. So it's at the called area, but after running the program, if you run printf, it will find the real address in the library space in the printf. So it does not say any kind of PLT. So that's the real printf address. Then what is PLT? So to call a function, a program needs to know the address. But at the compilation time, so this program runs on VMCTF2, and then it could run on your machine if you're running Linux, or it could run on the Windows subsystem on Linux on a different distribution of the Linux. Then it will have a totally different C library, but the program should work. So even if we don't know the exact address of the library, what it does is like at the compilation time, we have a placeholder for the gateway for those library functions. And these are PLT. And how it works is, so using GDB, you can examine what kind of assembly lines in there and print up. And if you examine as an instruction, then what it does is like it jumps to the content of this address. So what that means is that this address must store the address of printf. Yeah. So in the example, if you set R12 to this address, it will call printf. That's how the underlying system works. And then to examine this address with the values, if you do that, then you will see that the library function addresses are there. So basically, when your program is get loaded, you have a PLT at the fixed address. And then this table is called a global offset table. And then that will be filled with the real library addresses. So that's how the program can find the address of the printf at the runtime. So it's so-called dynamic linking. So how it works is that we have a PLT in the fixed area. GOT is in the fixed area too, because it's a data. That's why it is in a different area. And then how it works is like if we call PLT, then it jumps to the content of the GOT, and that's how we can call printf function. And visually, how it works is there's a global offset table, and then per each function, it will have the address to the real library address in libc. And then whenever a program calls printf, it calls a function in PLT. We don't care about the library. And then it will jump to GOT, and that's how we can find printf and any other library functions. Yeah. So GOT stores a libc address. And then how that works is actually, so this is the ideal case, but at the load time, so software designers are lazy. We don't load all the library address at runtime if we run it, because if we do so, then your initiation time will be slow because we need to resolve all the addresses at once. But have you heard about the amortize algorithm, those kind of things? So even if we need to do like n number of the process for the filling the library, what we can do is like we can fill the address at the first time you call the function, then like we can amortize that kind of overhead. So in system design, we use that. So at the start, when your program is get loaded, GOT always has the address of the DL dynamic resolved. DL here means that dynamic linking. Yeah. So when we call a printf for the first time, we don't know the address of the printf. Then it jumps to GOT. And then it will call DL dynamic resolve with printf. Then it will return the printf address here. We store that and call it. So the details of the global offset table is like it always have like all the entry as a DL dynamic resolve at first. And then after we call the function with PLT, then it will be automatically resolved, and then it will put the address there. Thanks to glibc. They do our job on behalf of us. And to do this, you can easily find the PLT address. Just open the binary with the GDB and then printf, print exactly those kind of thing. Yeah. But to find the GOT, you can use the pawn tools, or you can use the readelf information. So you can find GOT at there. Yeah. So the trick is, if you put this address without calling execve, then you will have no execve address. So what you need to do is, you need to call execve PLT with weird argument. It will fail. But that trial will make your program to store execve address to GOT. And then you can put this address to R12. Then it will run. Then now the R12 will point to the GOT of execve, and it will dereference that address of the execve. I know it's quite sophisticated, so please try this after solving all the challenge. Yeah, but you will see that I believe this is not as complex that some of the algorithm class homework or something. Yeah, it's just a step-by-step thing. Yeah, but if you control all the values correctly, yeah, then you can win. So the ROP6 challenge, there's no pop RDX, but you can control all the required register values using some other gadget. Yeah. And use that to call execve correctly and cat flag. Any questions for ROP6? Yes.
How would you call execve without it crashing? Like, call it once, populate the table.
So calling execve with without setting any kind of argument, it will return -1. It does not get segmentation fault. So just call it. And then that's for like filling the address. Yeah. And then there's another trick. If you set the environmental variable called the LD bind now, yeah, then it will bind all the addresses at the start. But that's a special case. But what I recommend is like just call it with weird argument. It will not crash. Yeah, it will just return -1. Yeah. And then that will fill the GOT address for you. Yeah. So it's quite neat. They will do our job for us. Yeah. Hackers need to be smart. Yeah. And now we know GOT. Then we can go for ROP5. So ROP5 challenge. And then there are some of the available functions. We have put, print, read, those kind of functions, but there's no open. There's no execve. And then it enabled the full ASRL. So, and then not about the binary program, but its entropy is like the 18, 19 bits or something. So you don't want to run that 500,000 times. Yeah. So there's a one-shot exploit. So I'm guiding that. So the exploit sketch of the ROP5 is that, so you can leak the address of the printf by printing the address of the GOT of the printf. Yeah. You can use print or write, puts, or those kind of thing. But the important thing here is that, so you want to use ROP chain to print this or that address as a GOT, then this printf call will give you the address of the printf. Then it will be same challenge as the ASR4. You know the address of the printf, then you can calculate the address, and then you can get the address of the exec BE. And then, so call printf the GOT of the printf, convert that address into the integer in the control script, calculate the base address, and then adding the offset to find the exec BE. Then you can run it. So once you understand GOT, then the ROP5 challenge is the same as like a ASR4. Yeah. But the interesting thing is, I got a lot of questions because, so when you try to print using printf to print the content of the printf GOT, take a look at this. The last byte is 0. That means if you put the GOT address, it will print nothing. So please, so if the printing on GOT prints nothing or less byte than 6 bytes, then you need to assume that there's a 0 byte. And then how you can avoid that is put the GOT address plus 1, then it will print 68B074A17F. Yeah. And then you can attach 0 at the end. Any questions about ROP5? Yeah, I know that you will ask a lot of questions in Discord, so it's okay. Yeah. So these are the exploit sketch, and then you can download the slide from the website. So, and then the due date is March 1st. So we have plenty of time, but I know it will consume plenty of time of you. Yeah. So please plan ahead, and let's have a exercise time.